It's a well-known theorem that complex roots of polynomials with real coefficients occur in conjugate pairs. So what this means is if you have some polynomial with real coefficients, such as a cubic polynomial with real coefficients, and you know that 3 plus I is a root, then its complex conjugate 3 minus I must also be a root. So first I just want to motivate this a little bit by thinking about quadratics. If we have a quadratic equation with real coefficients, if this has complex solutions, well, we know the solutions are given by the quadratic formula. So we know if there are two complex roots, they're given by this formula. And we know the only way, because a, b and c are real numbers, the only way this could be a complex number is if the discriminant is negative, and therefore the root of this negative number here will be an imaginary number. So, and because the plus minus is in front of this imaginary number, we're going to get a conjugate pair. Namely, if b squared minus 4ac is negative, we're going to get that the two roots are this. So we have the two roots are a complex conjugate pair. But then how are we going to prove this theorem in general? So this is just some justification for why it works for quadratics, but what about in general? Well, first of all, before we get to the proof, we need some properties of complex conjugation. So first, just want to state some facts. So if z and w are complex numbers, then it's true that the complex conjugate of z plus the complex conjugate of w is the complex conjugate of z plus w, and it's also true that the complex conjugate of zw is the complex conjugate of z times the complex conjugate of w, and it's also true if n is an integer that the complex conjugate of z to the n is the complex conjugate of z to the power n. So you might be wondering, well, how do we prove these facts? The first two I'm hoping you would be able to prove for yourself if you simply write z as a plus bi and w as c plus di, where a, b, c and d are real numbers. You should be able to prove these first two facts for yourself. This third fact is slightly harder to prove. One way to prove it would be proof by induction, which we haven't done yet, but or also perhaps using the binomial theorem, but I think an inductive argument would be best to show that this works for all integers n. Okay, but we're going to assume these facts. As I said, you might want to work through proving the first two, but we're now going to take these as a given and use these to prove the theorem. So we want to take any polynomial with real coefficients. So let's call our polynomial, if we let p of z be a subscript n z to the n plus an minus 1 z to the n minus 1 all the way down to a1 z to the power 1 plus a0, where all of these a subscript somethings, the ai's, are all real numbers. So this is a way of writing down in general some polynomial with real coefficients. And we want to prove that complex roots come in conjugate pairs. So we know if we let, let's say, let zeta in the complex numbers be a root of this polynomial p. What does it mean if zeta is a root? It means that p of zeta is 0. So we know p of zeta is an zeta to the n plus an minus 1 zeta to the n minus 1 all the way down to a1 zeta plus a0. This is 0. And now we want to show that zeta star, if we put that into P, we'll also get 0. So let's have a think about P of zeta star, the conjugate of zeta. So by the way, this complex number is called zeta, it's a Greek letter. So what would P of zeta star be? Well, it would be an times zeta star to the n plus an minus 1 zeta star to the n minus 1, way down to a1 zeta star plus a0. And we don't know what this is. So let's use this third fact to first move the stars outside and the powers inside. So we have an zeta to the n star plus an minus 1 zeta to the n minus 1 star, the way down to a1 zeta star plus a0. Okay, and then let's use this second fact to move all of the coefficients a1, a2, a3, a0, an inside the brackets, because the ai's are real numbers. So they're certainly complex numbers, so they certainly satisfy this second property. So let's move those inside. And then we have this sum. And a0 is the same as a0 star, because a0 is a real number. And then we have this sum, so all of these things are added together, so we can now use this first property to say this is the same as the complex conjugate of the entire sum, an zeta to the n plus an zeta to the n minus 1, all the way down to a0. And then, what is this thing inside the brackets? Well, it's P of zeta, isn't it? And we know that P of zeta is 0, because zeta is a root. So this is P of zeta star, which is 0, star, which is 0. So therefore, zeta star is also a root of P. And that concludes the proof.